Solve the linear program below using Dual Simplex. Minimize z is equal to 2x1 plus 3x2 subject to 2x1 plus x2 is greater than or equal to 3, x1 plus x2 is equal to 2, and all the x's are greater than or equal to 0.
Before we can perform dual simplex, it is necessary to have all the technological constraints be written as less than or equal to inequalities. First, we rewrite the equality constraint as two inequalities, one greater than or equal to inequality and one less than or equal to inequality. This leaves us with three inequality constraints. Next, we convert all the greater or equal to inequalities to the less than or equal to type by simply multiplying -1 to both sides and flipping the inequality symbol for each. Lastly, as in the simplex algorithm, we add the slack variables to each inequality, setting n minus m variables to 0, where n is the number of variables and m is the number of constraints. We have two non-basic variables. Remember that we conventionally prioritize decision variables first in choosing the initial non-basic variables, so these will be x1 and x2 for the iteration 1. The remaining variables s1, s2, and s3 are our basic variables. Now we can build our starting tableau. Note that entries in the objective function row are the additive inverse of the coefficients in the objective function. To perform dual simplex, it is necessary to begin with a solution that is both optimal and infeasible. Since none of the objective function row entries are positive for the minimization problem, the solution at this iteration is optimal. Furthermore, the solution is infeasible because there are negative entries in the right-hand side column. The requirements for dual simplex have been met, and we can begin the algorithm. For each iteration, we apply the dual feasibility condition, which is used to determine the leaving variable, and the dual optimality condition, which is used to determine the entering variable. According to the dual feasibility condition, the leaving variable is the basic variable corresponding to the row with the most negative entries in the right-hand side column, regardless of whether we are dealing with a minimization or maximization problem. Ties are broken arbitrarily. Our leaving variable here is s1 with a right-hand side entry of -3. After determining the leaving variable, we apply the dual optimality condition, which states that the entering variable is the non-basic variables column with the minimum absolute ratio between the entry in the objective function row and the corresponding constraint coefficient. Note that we may only choose from the constraint coefficients which have a negative value in order to ensure that the right-hand side will become positive, and thus feasible, after normalization for the iteration of the given algorithm. In this iteration, we are choosing between x1 with a ratio of the absolute value of -2 over -2, that is equal to 1, and x2 with a ratio of the absolute value of -3 over -1 is equal to 3. Thus, we select x1 with a smaller absolute ratio as our entering variable. Knowing our pivot row and pivot column from the leaving and entering variables respectively, we normalize the tableau using the following Gauss-Jordan row operations. Row 2, R2 prime is equal to R2 over -2. Row 1, R1 prime is equal to R1 plus 2R2 prime. Row 3, R3 prime is equal to R3 minus R2 prime. And row 4, R4 prime is equal to R4 plus R2 prime. Note that we always perform first row operations on the pivot row, since the new value in the pivot element will be used to zero out all other values in the pivot column. Our basic variables are now x1, s2, and s3, while our non-basic variables are x2 and s1. We arrive at the tableau for the next iteration, iteration 2, by swapping the pivot row variable s1 for the pivot column variable x1. We repeat the process of finding and leaving an entering variable for every iteration until the solution becomes feasible. All right-hand side column entries are non-negative. There is no need to check for optimality once the solution becomes feasible, since optimality is preserved by the dual optimality and dual feasibility conditions as the algorithm moves the solution iterations toward feasibility. For this problem, the dual simplex computation ends at iteration 3, with basic variables x1, s1, and s2. Therefore, the optimal solution to the problem is x1 is equal to 2, s1 is equal to 1, x2, s2, and s3 are all equal to 0, with z is equal to 4.